When the population standard deviation is unknown, we convert the random variable into a t-student value. It is similar to the z-value, but it follows a t-distribution. So in this video, I will focus on the t-distribution and the t-statistic. When the standard deviation population is not known, we use the sample standard deviation as an estimator. Thus, a normally distributed sample mean is then standardized using the t-statistic. And the formula to calculate the t-statistic is as follows, where S is the sample standard deviation and the others are just the same. X bar is the sample mean, mu is the population mean, and n is the number of sample. The random variable t follows the student t distribution, or more commonly known as the t-distribution, with n-1 degree of freedom, or in short, df. About the characteristic of the t-distribution, the t-distribution is actually a family of distribution, which are similar to the z-distribution in that they are all bell-shaped and symmetric around zero. However, all t-distributions have slightly broader tails than the z-distribution. Each t-distribution is identified by the degree of freedom, as seen in the diagram here. The degree of freedom determines the extent of the broadness of the tails of the distribution. The fewer the degree of freedom, the broader the tail. As df increases, the t-distribution becomes similar to the z-distribution. And when the degree of freedom approaches to infinity, it is identical to the z-distribution. Since the t-distribution is defined by the degree of freedom, it is common to refer it as the t-df distribution. So let's now learn about the t-value and the probability. This table provides the value of several t-statistics for selected upper tail probability and its degree of freedom. Since the t-distribution is a family distribution identified by the degree of freedom, the t-table is not as comprehensive as the z-table. It only lists probability corresponding to a limited number of values. Also, unlike the cumulative probability in the z-table, the t-table provides the probability in the upper tail of the distribution, as shown here by the green shaded area. Thus, for a random variable t-df, the notation t alpha, df represent a value such that the probability that t is greater than a value, a t-statistic, is equal to alpha. Or it says that the probability that t is greater than a value is equal to alpha. Similarly, t alpha divided by 2 df represent a value such that t is greater, the probability that t is greater than the t which is determined by an alpha divided by 2 and a degree of freedom. The probability area is alpha divided by 2. To determine the probability of a t-statistic, we need the significant level, or alpha, and the degree of freedom. A t-table will have the alpha in the uppermost row and the degree of freedom as the first column. The rest of the table is the value of the t-statistic. Now, suppose we want to find the value t with alpha 0.05 and the degree of freedom 10. Or we can write it as follows. Using the table, we look at the first column labeled df and find the row 10. We then continue along this row until we reach the column alpha equals to 0.05. The value obtained is 1.82, suggests that the probability that t with degree of freedom 10 is greater than 1.82 is 0.05. Due to the symmetry of the t distribution, we also get that t smaller than 1.812 is 0.05, the probability. Also, since the area under the entire t distribution sums to 1, we deduce that the probability of t, if we deduce this with 1, meaning this area on the left of minus 182 is 95%. And, or the other way around, the area, if we deduce 1 minus this area, meaning that p, the probability when p is smaller than 1.812 is just 1 minus 0.05, or 95%. Now that we have learned about the t distribution, when the population standard deviation is unknown, we will instead use the sample standard deviation and use the t statistic to replace the z statistic. Thus, the formula to construct the confidence interval is as follows, assuming that the sample mean is normally distributed, and S is the sample standard deviation, and the df is equal to n minus 1.